Mankind has always cooked food using everything from campfires and barbecues to gas and electric stovetops. Now he can use an induction cooktop. It doesn't need a fire, a flame, or a red-hot burner. It uses innovative cooking technology our ancestors never dreamt possible and would swear was pure magic. An induction cooktop doesn't use traditional cooking elements above or below the cooking surface. It uses copper induction coils that generate high-frequency electromagnetic fields. These fields excite the molecules in the pan, creating heat only in the cookware itself. That's why the yolk remains cold, and only what touches the pan cooks. The magic starts with a punching press that stamps computer-generated shapes into sheets of cold-rolled steel. These cutouts fix the position of the induction coils that sit under the glass surface. A press brake bends the four sides of the steel so it will hold a glass ceramic top in place. In the meantime, a machine spray paints the burner box, the visible part of the cooktop. A technician affixes the labels and the power cord onto a housing box that will conceal the induction electronics and coils. She secures the power cord for strain relief. She then attaches the power cord ground and the system ground wire to the housing box. She places a cover on the box and screws it into place. Another technician puts together the induction electronics. These assemblies of circuit boards, cooling fans, and semiconductors drive the cooktop. She covers the electronics with insulation and a metal carrier plate that will support the induction coils. Then she feeds the user interface wires through the top of the coil carrier plate. The technician screws the carrier plate and the electronic assemblies together, then grounds the electronics. Protective tape around the openings will prevent the user interface wires from rubbing against the coil carrier plate. And some insulation will protect the electronic assemblies. She closes that side of the electronic housing box and attaches all the power cables. A sheet of insulation goes on the flip side of the box, where she mounts the electromagnetic coil assemblies. The iron slugs on the back of each coil pod help distribute the electromagnetic energy to the cookware evenly. She connects the coil assembly to the system board. Then she places the remaining 4 coil assemblies onto the carrier plate and connects their leads to the system board. Meanwhile, another technician assembles the components of a glass touch user interface panel. She connects the interface to the steel holder that was bent into shape at the start and is now attached to the black burner box. She covers the cooking surface and control panel with an attractive stainless steel frame, then connects the system board to the control panel. She closes up the other side of the burner box. Then she bolts everything down to complete the cooktop. A technician tests the unit. Using a metal object to activate the electromagnetic field, he verifies that the controls respond properly. He makes sure all 5 induction coils are working and the power output from each coil is correct. The control panel confirms it's a success. Clean, safe, and energy efficient, induction cooktops make cooking food quick and easy. each transport truck on a road-level scale to calculate taxes on the goods it's hauling and to make sure the load doesn't exceed safety limits. You also find truck scales at grain silos, quarries, and other sites that move bulk products. The key to this enormous scale is a tiny component called a strain gauge, which sends signals to the scale's computer when compressed. They make the strain gauge from a laminate by bonding paper-thin sheets of nickel iron foil, epoxy, and Teflon in a press. Then they coat the laminate in a light-sensitive chemical and apply a plastic film with an image of strain gauges in negative format. Then they expose the setup to ultraviolet light. The light-sensitive chemical reacts, imprinting the images into the laminate's metal surface. Now they have rows of strain gauges. An inspector examines every gauge and marks any flaws to be discarded. Now, a technician measures how much voltage flows through each gauge. If it's too low, she raises it by rubbing off a microscopic amount of surface metal. When the strain gauges are finished, they cut them apart and send them to the load cell department. There, workers delicately tape 4 strain gauges into each stainless steel load cell. Then they solder electrical wiring to each one. The wires all run to a circuit board at one end of the load cell. And from the load cell, wiring runs to the scale's computer readout. The smallest amount of moisture or dirt would cause a strain gauge to malfunction, so they weld a cup over each one to hermetically seal it within the load cell. Every finished load cell undergoes a quality control check to verify that it works properly. The testing machine applies weight in increments until it hits the maximum weight the cell can bear, 34,000 kilograms or 75,000 pounds. The truck scale structure in which they'll install the load cells is called the weighbridge. They begin assembling it upside down with a surface made of steel plates. To build the base of the weighbridge, they lay out a grid of thick steel tubes and cross beams. Workers lower a guide to help them align the parts perfectly. Beneath each load cell is a pin. In order to weigh accurately, a load cell has to be level, so it's critical to make sure this pin is level before welding on the bulkhead that holds it. Once fully welded, the weighbridge is assembled and ready for painting. The paint equipment laces the powdered paint with a positive electrical charge, and the weighbridge with a negative one. This evenly draws the paint particles onto the steel like a magnet. In another department, they assemble the steel stand on which the load cell will sit. A welder tacks the pieces together, then a robot does the full welding. Now that all parts are ready, final assembly of the truck scale can begin. The weighbridge, right side up now, contains 8 load cells at different locations. The first step is to install each load cell stand into its respective position. They insert a link on each side of the stand. They position the load cell at the top of the links and the bulkhead pin at the bottom. Then they close up the location with an access plate. The last step is to calibrate the scale. They lay a 10,000-pound weight on different parts of the scale to check if the digital readout is accurate. It takes a lot of time to get a truck scale just right, but it's definitely worth the wait. For for up to a year without refrigeration or the use of additional preservatives. Made mostly from paper, they're recyclable into things like egg cartons, paper towels, and toilet paper. A Tetra Pak container is packaging built with nature and freshness in mind. Tetra Pak containers hold all sorts of food products from smoothies to fine wines. The package gives products a long shelf life because of its special layers. The plastic layer, the paperboard, and the foil. A plastic coating makes the package leak-proof. Tetra Pak containers are made entirely from recyclable materials. The first step to making them is printing. A worker selects the appropriate printing plates for a given customer and applies them to the cylinder of the printing press. The press transfers one color at a time to the paperboard layer using solvent-free ink. A Tetra Pak container can have up to 6 colors. At full speed, it takes only minutes to print. A strobe light visually stops the motion, helping the pressman check the quality of the printing. A worker feeds the printed paperboard into a lamination machine that will join it with the plastic and foil layers. At the same time, the worker loads a roll of micro-thin aluminum foil into the laminator. A gas flame heat treats the paperboard to ensure adhesion to the plastic layer. The laminator extrudes liquefied plastic between the roll of aluminum and the heated paperboard. Rollers squeeze all the layers together. The printed paperboard, with all its protective layers applied, then comes off the back end of the laminator in a large master roll. The operator threads it into a cutting machine called a slitter. It cuts and winds the printed material onto individual rolls. The slitter's knives cut the material into 4 lanes, each of which becomes a smaller roll. The operator trims the excess material from each roll. Then a conveyor system sends the rolls for shipping to a packer to be filled with their product. At the packer's plant, an operator loads the roll of flat packages into a filling machine built and installed by Tetra Pak. Tension rollers guide the material into the filling machine where it is sterilized. The machine then forms and seals the material into one continuous tube. And a little further down, the machine fills the tube with product. It then cuts the tube into individually sealed packages and drops them into a chute for folding. It ejects the finished packages onto a conveyor belt. Finally, it sends the packages on their way to the customer. Lightweight, compact, and recyclable, Tetra Pak containers are eco-friendly. And that's certainly something to celebrate over a glass of fine wine. There are two main types of harmonicas. A diatonic harmonica has 10 mouth holes. It plays a 7-note major scale in a single key of music. A chromatic harmonica has up to 16 holes, plus a special slide mechanism to produce extra notes, so it can play in any key. As air goes through a harmonica, so does saliva, which is why they make the inner structure from a type of wood that doesn't expand or smell with repeated exposure to moisture. Making a standard chromatic harmonica begins with a block of pear wood measuring about 5.5 by 1.25 inches. They run it against a cutter that carves a row of air chambers front and back. This produces the component known as the comb. A press stamps slots in a millimeter-thick brass plate that will hold the reeds. The plate will eventually go on top of the comb, its slots aligning with the comb's air chambers. Another machine cuts reeds from brass-based metal, specially formulated by this company to produce quality sound and be corrosion-resistant. Working one size at a time, they cut a batch of a few hundred reeds. They test a reed from each batch with a tuning machine, plucking it to see if it produces the correct pitch. The size and profile of a reed determines the note it produces. The longer it is, the lower the note, and vice versa. Now they rivet the reeds to the reed plate, one reed for each note. Consecutive reeds go on opposite sides of the plate. With this configuration, blowing into the harmonica vibrates one reed, while drawing air out vibrates the other. They flatten each rivet on one side of the plate. This fastens the reed securely at the bottom, leaving the rest free to vibrate. If necessary, they file the reed down, so the slot doesn't obstruct its movement. Now a tuning specialist gets to work. She plays each reed on the plate and compares the tone to a perfectly tuned set of reeds for reference. If the pitch is off, she adjusts it with a bit of filing. Once the reed plate is in tune, it goes on top of the comb, the reeds and slots aligning with the comb's air chambers. Workers attach the parts with steel nails that have a brass plating to prevent corrosion. Now for the two-piece cover that encloses these internal components. For standard models, the factory uses stainless steel, starting with a sheet that's less than 0.5 millimeter thick. Fancier harmonicas have silver or gold-plated covers. The sheet goes through a press that has a series of dies. They progressively stamp out the cover pieces, first embossing the artwork, then cutting the size, then forming the shape. Workers sandwich the comb between the two cover pieces, then attach everything with either brass-plated nails or brass or nickel-plated screws. Chromatic harmonicas have a mouthpiece over the blowholes. It's usually made of chrome-plated brass that they curve slightly in a press. The mouthpiece shields the lips from a slide mechanism inside. That mechanism has 3 parts, a slide with a button positioned in between 2 plates. They screw the mouthpiece onto the front of the harmonica. When you press the mouthpiece button, it redirects the air, raising the notes half a tone. No harmonica leaves the factory without a sound test. Rather than blow into every instrument, the testing department uses a machine that blows air in and out. Last stop is the cleaning department. There, workers inspect for scratches, then polish and package, so that each and every harmonica will look as good as it sounds.